I want you to imagine a rock. Simple enough. The rock you're imagining is actually part of the bedrock. And since it's visible on the surface, that also makes it pretty large. About the size of a house. It's definitely not the pebble you find on the sidewalk, but at the same time, nothing unfathomable. Then again, you are looking at it give or take 100,000 years ago. Over the millennia, despite the best efforts of wind and water to tear it apart, this rock has grown into a colossus. A titanic mound of stratified rock thousands of meters tall and tens of thousands wide at its base. It eclipses our largest skylines in size and our greatest civilizations in age. When this rock began its journey, it could have been moved by human hands, albeit with some difficulty. But today, this rock with a mass of billions of metric tons is going nowhere anytime soon. To move this rock would require an immense amount of energy, a single event more powerful than anything in mankind's arsenal. And an explosion of this magnitude would be nothing short of a cataclysm. But just for a second, imagine that it actually happens. Although volcanoes are somewhat misleading. About 60 miles to the southwest of Tokyo lies arguably the single most picturesque volcano in the world. A symbol of the nation's culture and a mainstay in Japanese media, this is Mount Fuji. And if there was ever an image to accompany the word volcano, this is it. Conical shape, hole at the top, and massive size making it visible for a great distance. Fuji, however, isn't the volcano. At least when talking specifically about Mount Fuji as the mountain, a massive elevated mound of rock. A volcano doesn't require a mountain to accompany it to be a volcano. Really, a volcano is just a vent or other opening in the Earth's crust that allows hot material from the interior, be it magma or trapped gases, or both, to exit out onto the surface. Mount Fuji is simply the product of thousands of years of these expulsions. It is the facade that hides the volcano at its heart. These facades, mounds and mountains produced by volcanism, come in a variety of shapes and sizes, and are heavily dependent on the chemical composition and temperature of the volcano's magma. Enter the spectrum.
Get Spectrum TV for only $29.99 a month.
Of igneous rocks. It's time for some middle school earth science. Igneous rocks, that is, rocks produced by the cooling of magma and lava, are categorized in several ways. but the one that matters in this case is the rock's silica content. Silicon dioxide molecules, because of the specific bonds silicon and oxygen form, are really good at forming bonds with neighboring silicon dioxide molecules, a process called polymerization. What you get as a result is a network of interconnected silica which holds itself together quite well, and plays a central role in determining the viscosity of its magma or lava. Igneous rocks with higher silica percentages are described as felsic, and it's over here where you find rocks like rhyolite and its coarse-grained intrusive counterpart granite. Rocks with lower silica percentages, down around 50%, are described as mafic, and this includes rocks like basalt and gabbro. Now, this isn't a dichotomy. In between the two you have andesitic rocks like andesite, and over on the far end are ultramafic rocks like peridotite, which has a similar composition to the Earth's mantle. But the point here is that volcanoes of felsic origin are going to have magmas with very high viscosities, and thus will want to cling to itself. Now, with that, and the fact that rhyolitic magmas typically cool faster, and you tend to end up with volcanic cones with relatively steep slopes. Continue to add magma to the sides, slowly stratifying each successive layer, and you get an incredibly tall and imposing monolith, a stratovolcano. So naturally, the flip side of this for volcanoes with mafic basaltic magmas are going to be runny, flat, pancake-looking things. But this isn't always the case. There is a way to produce a steep volcanic cone with less viscous magma, and that is by increasing its quantity of volatiles. A volatile is really just a fun way of saying gas that is trapped within the magma. Gases like water vapor, carbon dioxide, and a host of others. Now, the tendency for gases, especially gases that are extremely hot, is to expand. So volatiles exert outward pressure on the magma, increase the quantity of volatiles, and this pressure goes up. Now, down deep in the Earth's crust, the inward pressure of the surrounding magma and rock is able to counteract this. But as the magma makes its way up, this inward force diminishes. Eventually, it reaches the surface as lava, and if the outward force of the volatiles is great enough, it will push the lava apart, scattering it into little droplets. These droplets then cool very rapidly as they fly through the air into tiny chunks of rock called cinders, hence the name of this specific type of volcanic cone. Being steep, however, does also come with some limitations. The surface of a cinder cone volcano is not unlike that of a pile of sand, and thus its slopes are shaped by the individual cinder's angle of repose, which is basically just the point at which gravity is able to overcome the cinder's ability to grip themselves, causing them to slide down. This means that all cinder cones have slopes of around 30 degrees, give or take a couple. The composition of a cinder cone, with the surface being a granular material and the interior being a quasi-igneous sedimentary rock, also means that they are heavily influenced by erosion, which can often put a cap on their size and longevity. Some of the tallest cinder cones on Earth can reach heights of 1,000 feet or greater, which is definitely tall on a human scale, but relative to their stratovolcanic cousins, not really. About 3.5 miles northeast of the Tokyo skyline sits this massive thing, the Tokyo Skytree. It is the tallest freestanding tower in the world, and the third tallest object mankind has ever built up until now. At 2,080 feet tall, it is the closest thing Japan has ever constructed to challenging Mount Fuji. But closest is the key word here, because even one of the tallest structures in the world is pitifully small next to the volcano, whose peak soars to nearly 12,400 feet. The highest mountain in Japan, Fuji is on the larger size of stratovolcanoes in the world, and its imposing size has undoubtedly contributed to its extensive notoriety. An equally famous volcano, but not necessarily for the same reason, is Italy's Mount Vesuvius. As the backdrop to Naples, it can be equally as imposing. But Vesuvius is comparatively small, with its current volcanic cone reaching a height of only 4,200 feet. For an Italian volcano of equal size to Fuji, Sicily's Mount Etna is quite a bit closer, and happens to be one of the most active stratovolcanoes in the world. Although large, however, neither Fuji nor Etna are the biggest of their kind. So what is? What is the largest stratovolcano? Seems like it would be fairly straightforward. You ask Google what the tallest stratovolcano is, and it spits out a big mountain. Like with many things, however, it's not. And that's because attempting to answer this question quickly runs you into one that's even harder. The Everest question.
Believe it or not, we've got more of this in Saturday. So don't you dare leave me here alone. We're heading straight to the north base of the
The peak of Mount Everest rises to an altitude of 29,000 feet above sea level, the highest point on Earth relative to it. It is the furthest one can travel up into the atmosphere without outright flying. So high, in fact, that even at latitude 27 degrees north, where its boundary is significantly higher up than over much of the United States or Europe, the stratosphere is still closer to Everest's peak than sea level. Ask how high Mount Everest is, and you can get a fairly definitive answer. Ask how tall Everest is, however, and that answer quickly decomposes into a mess of competing potential measurements. When measuring mountains, there are typically three: elevation, prominence, and base to peak height. Elevation is pretty straightforward. How high does the mountain's peak reach up into the atmosphere? You take a meter stick, or several thousand, and measure the distance between sea level and the top. This is generally how mountains are measured, and where we get the 29,000 foot figure for Everest. The issue with this, of course, is that elevation may or may not include height that most would struggle to consider part of the mountain. For example, let's say you're standing in the middle of northern nowhere, Iowa. It's flat. Really flat. The perfect place to put a 50-foot pile of boulders. Except it wouldn't be 50 feet tall according to elevation, because that flat nothingness you're standing on is 1,100 feet above sea level. Therefore, your pile of boulders is actually 1,150 feet high. And the same is true for Everest. Mountain prominence attempts to rectify this to a degree by looking solely at the vertical rise of a mountain relative to higher peaks around it. Prominence measures a peak's height by looking at the lowest point between it and its closest higher neighbor, and subtracting said lowest point's elevation from the peak's elevation. Now, because mountains aren't just 2D silhouettes, there are multiple low points between peaks forming a saddle. Thus, the top of the saddle is used. Think of it as the highest of the low points, if that makes any sense. The use of prominence makes fairly drastic cuts to otherwise incredibly high mountain peaks. Giants like Kanchenjunga or the Karakoram Mountains K2, both with peak heights of over 28,000 feet, suddenly drop to below 15,000. Now, because prominence works in relation to a peak's higher neighbor, it becomes somewhat of a chain. Broad Peak in the Karakorams is a 5,600-foot sub-peak of Gasherbrum. Gasherbrum is a 7,000-foot sub-peak of K2. K2 is a 13,000-foot sub-peak of Everest, and... well, we've run into another problem. Everest doesn't have a parent peak, and therefore its prominence defaults to its elevation, 29,000 feet. Well, that's not going to work. And this is an issue that not only affects Everest, but all highest peaks of their respective mountain ranges, especially those separated by oceans. So, while prominence does give a more accurate figure for how tall a mountain is usually, it is certainly more specialized than elevation. The specialization of prominence is what base to peak height therefore attempts to rectify. Base to peak height is also as it sounds. Where is the mountain's base, where is its peak, and what is the vertical distance between them? By this metric, the 50-foot pile of boulders is 50 feet tall. Plain and simple. Measuring by this way, however, isn't perfect either, chiefly because it's often difficult to pinpoint exactly where a mountain's base is. While the Himalayas were indeed formed by tectonic uplift, that uplift aided in the formation of glaciers, which then carved out massive ravines along the flanks of the peaks. It's fairly clear-cut when the pile of boulders is out on the flat plains of Iowa, but what happens when you put it right up against the Grand Canyon? Where's its base then? Most would probably still say it's only 50 feet tall. And that's why, from a geographical topographical point of view, the average height of the Tibetan Plateau is arguably the best elevation for Everest, making it shorter overall than exceptionally tall mountains like Denali, or those with massive immediate vertical rises like Rakaposhi. Everest, of course, is not a product of volcanism, but as it should be obvious by now, the world's highest volcano shares a similar predicament. Welcome to the Andes, home to the highest mountain peaks in the world outside of South Central Asia. Officially, the tallest volcano on Earth resides here. The second highest peak in the chain, Ojos del Salado, on the Argentine-Chilean border. While its peak rises to an impressive 22,615 feet, Ojos del Salado resides 140 miles inland at the heart of the mountain range. The base of the volcanic cone flattens out, in reality, only about 7,600 feet below that. This means that the highest volcano on Earth is shorter than a plethora of other volcanoes. Fuji and Etna, whose bases are both very close to sea level, Mount Rainier in Washington, Mount Elbrus in Russia, or even its Andes cousin Chimborazo in Ecuador, which, yes, happens to be the highest mountain on Earth when measured from its peak to the Earth's core. There, I mentioned it. Moving on. So the altitude of the peak alone isn't going to give us the largest stratovolcano. The peak not only has to be high, but the volcanic cone itself has to sit on ground with low elevation relative to sea level. When given this limitation, there's really only one that immediately stands out. Another of the world's most visually stunning volcanoes. A single solitary titan rising from an unlikely location. Tanzania's very own Kilimanjaro's size is very easily understated. It's among the 7 summits of the world, meaning it is the highest mountain on the entire African continent. And yet, it doesn't call a mountain range home, but rather extends upward directly from the savanna around it, which has a mean elevation of around 3,000 feet. This gives Kilimanjaro a colossal base-to-peak height of just over 16,000 feet, which is nearly 5 kilometers tall. Not high, tall. Its base is nearly 40 miles, that's 64 kilometers wide at some points. It is absolutely gigantic. It completely dwarfs all of the world's most striking stratovolcanoes, and the craziest part is, it's not even the world's largest volcano.
What did you say?
Alright, let's wind back a bit. Basaltic magmas with a low percentage of volatiles tend to erupt from their parent volcanoes as a runny, fluid mass of lava which flows without effort. And basaltic magmas as well tend to be significantly hotter than their rhyolitic counterparts. Thus, volcanic cones produced by these volcanoes aren't really going to be cones, more so big flat slabs that cover a large area, not very efficient at growing in height. However, that's only if you let the air do all the work. Give the cooling job to water, and suddenly lava is able to build up significantly faster. So fast, in fact, that suddenly you have some of the single largest volcanoes on the planet. and none are bigger than the Big Island itself. The island of Hawaii, in the Hawaiian island chain, is home to 3 prominent volcanoes. Except, it's not. It is 3 volcanoes: Kilauea, Mauna Loa, and Mauna Kea, the latter of which has been fighting with Everest for the title of world's tallest mountain for decades. In terms of elevation, the Hawaiian volcanoes are nothing special. 13,803 feet from Mauna Kea, with Mauna Loa trailing it by a mere 125 feet. Their peaks are about as high as the Cascade stratovolcanoes. However, the Hawaiian volcanoes don't break through the crust on the shelf of a continent. They do it on the seafloor. Thus, their volcanic cones actually begin nearly 17,000 feet below the sea surface, making them by far the tallest mountains on Earth. Mauna Kea's peak leads the two in height, but it is Mauna Loa's cone that makes up the vast majority of the island. Again, though, calling it a cone isn't exactly accurate, as its flat slab appearance hardly resembles the sharp striking slopes of a stratovolcano. The Hawaiian volcanoes are more akin to a flat dome, not unlike that of a shield. Hence, their classification as shield volcanoes. This means they are not only tall, but also gigantic in terms of their diameters. The shield of Mauna Loa is so massive and so heavy that it crushes the Pacific plate below, deforming the lithosphere it sits on. The shield volcano reigns unchallenged as the largest of the volcanic mountains, and that's not just on Earth. Olympus Mons on Mars, the single largest mountain in the solar system, is also a shield volcano. There, I talked about that. Moving on. On the flank of the giants Mauna Loa and Mauna Kea, however, sits their smaller sibling of Kilauea. It is incredibly active, flanked by spatter cones and rifts in the crust, all centered on a massive crater in the center. Volcanic craters are another key attribute of many of the world's volcanoes, but Kilauea's is a very particular crater. Unlike the blast craters of Fuji or Vesuvius, Kilauea has a caldera, meaning it was formed from the collapse of surface material down into the void space once inhabited by magma. Mauna Loa also has one, connecting its 2 major magma rifts, and calderas are the primary geographic landform associated with the largest volcanic systems on the planet. Heavy hitters like Long Valley in California, Taupo in New Zealand, the gargantuan Lake Toba in Indonesia, and yes, Yellowstone. But while these are volcanoes, they're really just big stretches of volcanically active land, and from first glance don't capture the imagination like the tall cones of other volcanoes, or even the gradual rises of shield volcanoes. When it comes to combining these 2 quintessential features of a volcano, craters and cones, there's only one volcano that, in my opinion, whatever that's worth, is truly exceptional. Mount Tambora is incredibly deceiving. Its gentle slopes extending from the ocean around it on what is very close to being an island suggest a wide but relatively short volcanic cone. This couldn't be further from the truth. In actuality, Tambora is immense. It's over 25 miles in diameter, and the highest point along its rim extends up to 9,300 feet. And that's 9,300 feet from sea level, making it only slightly shorter than other large stratovolcanoes. Its lost peak, once soaring to over 14,000 feet, has since been replaced by a near-circular caldera. A caldera which, mind you, could very nearly swallow Mount Vesuvius whole. It is the end result of Tambora's infamous 1815 eruption. Remember for aiding in global famines and nearly stealing an entire season? An eruption so powerful it cut one of Indonesia's largest mountains down by a third. An eruption that ejected so much material from the earth that the top of Tambora sank into a hole the size of Boston. Today, the caldera of Mount Tambora is a reminder of that, and simultaneously is the most prominent physical glimpse we have of the mechanisms that power it down below. But it is only a glimpse. The power plant of a volcano is a vast network which extends to distances far beyond that of any individual mountain. And believe me when I say even a colossus like Tambora is only the tip of it. Earth is a big ball of stuff, which means that at some point, a bunch of stuff had to come together to form it. Nebulous dust around the early sun collected into grains, which then collected into rocks. Big rocks, weighing millions, some billions of tons. The fun part is, to orbit the sun, you need to be going pretty fast, which means these colossal boulders have quite a bit of kinetic energy. And when they smashed into each other, that kinetic energy gets turned into thermal energy. Thus, the early Earth was incredibly hot. A massive molten ball of silicates and metals which slowly began to separate by density. Iron and nickel sank to the core, while lighter materials floated on the surface. When these lighter materials finally cooled, they formed the crust, the thin, solid outer skin of the Earth. However, this meant the incredibly hot interior of the Earth was now insulated from radiating its heat out into space, which is an already slow process. And the radioactive materials attempting to release their own energy were now trapped. Throw in the massive pressures involved with quadrillions and quadrillions of tons of material pressing inward from gravity, and what you get is an incredibly hot core, a partially melted mantle, and a cool solid crust. There is a huge, very unstable temperature disparity here. Warmth does not like to be below cold, and thus this opens the door for the return of our good friend, convection. Convection is a process that permeates all fluids. In the atmosphere, it helps grow thunderstorms. In the ocean, it helps generate currents. And it's why if you put an ice cube or two in your hot chocolate, it actually helps it mix better. Go ahead, try it. I'm not kidding. While the mantle of the Earth is not liquid, it is still very malleable. Think Play-Doh. It is therefore able to move like a fluid, and is heavily influenced by convection. Just like in the atmosphere or the ocean, the mantle is full of convection currents. They're slow, but they're there, and the crust of the Earth is constantly being wrenched around by them. Yeah, you see where this is going. Okay, so the Earth's interior is incredibly hot. How do we make volcanoes out of it? Well, there's 3 ways. Again, a volcano is just an opening in the crust. So the easiest way to make a volcano is really just to take 2 opposing convection currents and
literally rip his...
The mid-oceanic ridges that line the bottom of the world's oceans were formed in this manner, which the famed volcanoes of Iceland are also a part of. Because of this, they are technically the largest volcanic systems on the planet. So eat your heart out, supervolcanoes. The second way is actually to do the opposite. Slam plates together. It has to be a specific combination though. Slam 2 plates of equal density material together and you get the Himalayas. But converge 2 of differing density, say the heavy compacted ocean floor and a lighter continental shelf, and you get subduction. The subduction zones of the world are most well known for their association with giant megathrust earthquakes, and the historic tsunamis that have followed them. However, volcanoes can be just as much a product of subduction as they can. The ocean floor is not uniform, topographically or geologically. It is a sandwich of varying layered materials, and not all of them have the same melting point. In addition, the ocean floor also absorbs seawater. Couple these two together, and when the plate finally subducts into the hot interior of the Earth, pockets inside it will begin to expand and melt. Eventually it bores its way out of the plate and begins its rise above the denser surrounding material. And upon reaching the continental plate above, it melts a hole in it. When that magma reaches the surface, you have a volcano. The third way to make a volcano is pretty much just to do this, but without melting a tectonic plate, and the process 4. Now, there's a few competing theories on how to actually achieve this. One postulates that natural tension exerted on a tectonic plate will cause rifts and fractures to occur along its base, allowing magma from the upper mantle up into the crust. The leading theory, however, relies on mantle plumes, massive convective upwellings of mantle material superheated by the Earth's outer core. When these plumes reach the bottom of a plate, the plate begins to melt, forming pockets of magma which make their way to the surface. Whichever theory you subscribe to, this is a hotspot, a point of volcanism free from the ties of plate interactions, sometimes thousands of miles from the nearest plate boundary. This is how the Hawaiian volcanoes were formed, and dozens across the globe. Whether it be subduction or a hotspot, boring a hole in the Earth's crust is not a simple endeavor. Magma gets stuck, it cools, remelts, and shifts around along its journey. And this leads to pockets inside the crust where magma pools together. Magma chambers are seldom what they are typically imagined to be, a single, cavernous pit with hot, glowing liquid rock. In reality, they're more often networks of partially melted magmatic masses linked by branches and vents. In several cases, depending on how active the volcano is, they may even be completely solid. However, to say they aren't cavernous would also be untrue. The internal volume of a magma chamber is still quite impressive, and the depths they can reach even more so. Now, actually measuring these depths is a practical impossibility, by traditional means. The good news is we don't actually have to dig down there with our rulers and tapes to do it, because something else is already down there. Energy. Kinetic energy. Emitted from another not-so-friendly source. There's a great irony here. One natural hazard enables us to study another, but it is true. The energy produced by earthquakes is a great tool for mapping the interior of the Earth. Deep seismic waves, those are your compression and shear waves, change their velocity, that's both speed and direction, with changes in density, drastically when moving from a solid to a liquid. And in the case of S waves, well, they don't move through a liquid at all. So if you have a seismic sensor on one side of a volcano, and you record the arrival times of seismic waves from an earthquake on the other side, or for S waves, whether they show up at all, you can figure out what's down there. Do it with hundreds of sensors, thousands of quakes, and you can create a map. This is the magma chamber network of Mount Vesuvius. It extends well over 100,000 feet below the surface, that's over 30 kilometers, far beyond the deepest oceanic trenches or man-made boreholes. While a thoroughly mapped magma system like this is uncommon, these great depths are not, and Vesuvius is a far cry from having the largest magma chambers on the planet. That is a title which unceremoniously belongs to the Yellowstone caldera, whose magmatic sources have been studied, restudied, and then studied one more time for the hell of it. Yellowstone sits on two distinct magma chambers, reaching depths of nearly 50 kilometers. The shallower of the two having a total volume of 10,400 cubic kilometers, and the lower chamber having a volume 4.5 times that. Together, they contain a greater volume than the entirety of Lake Erie. And Lake Ontario. And Lake Huron. And Lake Michigan. And, yes, Lake Superior. And Lake Victoria. And Lake Baikal. And the Grand Canyon. And even with all of that, and yes, I mean combined, you're still about 4,000 cubic kilometers short. The good news is that only a small fraction of Yellowstone's magma chambers are actually molten, and its larger, lower chamber is actually mostly basaltic, non-explosive basalt. Comparatively, Yellowstone's magma systems are actually pretty quiet at the moment. There are a host of other volcanoes around the world that are far more active, perhaps not with the same scale as something like Yellowstone, but volcanoes with a far larger quantity of molten material down below them, with a far more volatile composition. There are those that are waiting, building, buying their time before they can erupt. And then there are those that have already made a name for themselves.
This is the CBS Evening News with Morton Dean.
Good evening. There was a violent explosion of a different kind early this morning in the Pacific Northwest. Washington State's Mount St. Helens blew her top once again. And police report that 5 people in an area north of the mountain apparently died when they inhaled the burning hot
The days and weeks following May 18, 1980, in the areas north of Mount St. Helens would have seemed otherworldly. Without context, it's doubtful you'd even believe this was America's Pacific Northwest, a region defined by its vibrant evergreen forests, pristine lakes, and white-capped mountains. A far cry from that, this is a barren wasteland, caked in mud and ash, the carcasses of fallen trees lining the hills, and the deformed silhouette of Mount St. Helens residing over all of it, its peak replaced by a blast crater 2 kilometers in diameter.
I've never seen or heard of anything like this before. Somebody said it looked like a moonscape, but the moon looks like a golf course compared to what's up there. It is a horrible-looking sight.
This is the hell a stratovolcano can unleash, the result of months of magmatic buildup below the surface. On the morning of the 18th, a shallow earthquake below St. Helens triggered the collapse of its peak and north face in the largest landslide in recorded history. A massive rock the size of a city slid down the mountain, uncapping the pressure-sealed magma below it. The subsequent eruption rapidly buried the mountain and surrounding areas in ash, as pyroclastic flows swept over forests, roads, and the occasional nearby structure. The 1980 eruption of Mount St. Helens concluded with a total energy release of over 100 billion megajoules. That's a 24 megaton TNT equivalency. But even numbers like those don't fully describe the dynamic destructive forces of a large stratovolcanic eruption. Natural disasters operate on such a comparatively large scale to us big-brained apes that it's often advantageous to categorize individual occurrences. A number of natural hazards have their own scales, assigning categories based on whatever the scientists who study them feel is the most important component. For hurricanes, there is the Saffir-Simpson scale. For earthquakes, the moment magnitude and modified Mercalli scales. And for tornadoes, the enhanced Fujita scale. Each basing its ranking around a specific attribute. And despite being dynamic processes, that attribute is usually pretty obvious. But what exactly are you supposed to rank a volcanic eruption on? And then, how do you measure it? Do we measure the eruption based on duration? Perhaps the size of the cloud produced, or the amount of debris shot out? Well, there is an official way to rank eruptions, championed by the one and only, the VEI, the Volcanic Explosivity Index. The VEI attempts to categorize eruptions based on... Okay, so apologies to all the volcano enthusiasts in the audience, but the VEI is a clusterfuck. The VEI ranks volcanic eruptions on everything, or just about. If we want to apply its methodology elsewhere, the best comparison I have is if we were to take the enhanced Fujita scale for measuring tornadic damage, the British Toro scale for measuring its wind speed, the old Pearson scales for measuring other quantifiable metrics like size and travel distance, then tack on semi-official descriptors of appearance, because why not, and then on top of all of that, go around to random witnesses and ask them to describe it. See if they call it violent, or scary, or big. Take all of these, put them into a blender, and you have the tornado equivalent of the Volcanic Explosivity Index. Now, this isn't to say the VEI is bad, of course. It's a clusterfuck, yeah, but it's a clusterfuck in the same way complex integration is. Those who use it do it to great effect, and it's served its role well since the early 1980s. And while the VEI does take several parameters into account, there is absolutely a hierarchy of sorts. The most prominent of the eruption attributes the VEI looks at is ejected material. How much stuff was belched out? Ejecta is measured by dense rock equivalency. Essentially, if you were to take all the ejecta, the ash, the volcanic bombs, etc., and pile them together into one big, solid block of rock, free of pores and gas pockets, how big would that cube be? Mount St. Helens 1980 blast scored it a VEI 5, with a total DRE of ejected material sitting somewhere between 0.25 and 0.5 cubic kilometers. On the 8-tiered scale of the index, 5 ranks quite high. As always, however, there is an asterisk hanging over all of it. The VEI, at least in terms of DRE, works on a logarithmic scale, much like the moment magnitude scale for earthquakes, meaning that, on the average, each tier on the index will eject 10 times as much material as the previous. 3 steps up on the VEI is the top of the scale, the rare and immense VEI 8s. Gigantic eruptions like Taupo and Toba, releasing not cubic kilometers worth of material, but thousands of cubic kilometers of material. DRE cubes so big, they would eclipse actual mountains. But ejected DRE is not the only metric the VEI considers. The 1944 eruption of Vesuvius released a similar amount of material as St. Helens in 1980, and yet it is considered to be a VEI 3, and its older, more infamous 79 AD eruption, a high-end VEI 5, released material several times that of St. Helens. Down a step in the VEI's hierarchy is seemingly what you'd expect given the index's name: explosivity. A key attribute of any large Pleiadian-type eruption is it's violent. But as with any explosion, it's difficult to gauge without knowing the store of potential energy it drew from. With a bomb, this is the amount of reactive material, which is obviously known as the bomb had to be assembled. With a volcanic eruption, this is the contained pressure being exerted by the magma and the gases it holds. And that very specific force usually isn't quantifiable. Thus, the explosivity has to be measured indirectly by observing some other feature. And this is where things really get interesting. A more powerful explosion is naturally going to propel things faster. Confine those things in a tube, say the barrel of a gun or a volcano, and said things will generally be propelled in one direction. In most cases with a volcano, this is up. Gravity will naturally want to bring things down, but the point is the more explosive an eruption, the higher the eruption column, regardless of the total amount of material ejected. Two volcanic eruptions can release a similar amount of energy, but if one takes hours to complete, while the other takes minutes, the latter is more explosive, and therefore will create a taller eruption column. Assuming it explodes upward, of course. St. Helens is a bit of an exception here. Much of its eruption was lateral, as the landslide uncovered the north face. Still, the initial blast and heat of the eruption was enough to propel its column skyward to nearly 25 kilometers, over 82,000 feet into the atmosphere, several kilometers higher than even the largest North American thunderstorms. But St. Helens is hardly the winner in this category either. Vesuvius erupted to heights of over 30 kilometers, as did the 1912 VEI-6 birth of Nova Erupta in Alaska, and the gigantic VEI-7 eruption of Tambora shot material up to well over 40. But VEI rating is no guarantee of explosivity, and even titans like these pale in comparison to the true king in this regard. An eruption so instantaneously violent, it was heard around the world. Arguably the single most famous volcanic eruption in human history.
When lava pours out near the sea surface, tremendous volcanic explosions sometimes occur.
All right, let's get it out of our system.
Captain Magma! Get him angry and he's bound to erupt! Krakatoa!
For many, this may very well be the first time its name was ever heard. I know it was for me. But if someone is going to study volcanoes and their history, it's pretty hard to miss, for very good reason. Krakatoa has changed significantly since its 1883 eruption. Sitting nearly 100 miles west of Jakarta, it is one of Indonesia's premier attractions. Regularly active, mostly harmless from a distance, and rising gently out of the water. It doesn't immediately scream killer. Except, that's not Krakatoa. Krakatoa is actually over there. The active island that partially blew itself up in 2018 is Anak Krakatau, translated as Son of Krakatoa, a small volcanic cone grown from the same vents that once fed Krakatoa itself, which sits to the south, or at least what's left of it, the charred corpse of a once proud island. What is today 4 islands was once only 3, Krakatoa the largest of them. This geographic configuration that stood for hundreds of years prior was itself the product of a previous large eruption, the collapse of the caldera breaking the 3 islands apart, leaving Krakatoa to grow in the center. Though, in the months of mid-1883, sporadic yet increasing volcanic activity began to rock the island. This continued until late August when... gone. 70% of the island. The only thing remotely comparable is the destruction of Pacific Atoll Islands during nuclear testing. But these aren't the sandy flats of Alujilab. The volcanic cones of Rakata, Denon, and Perbuatan were massive mounds of rhyolite, together forming an island 100 times larger, weighing millions of tons. On August 27th, 2 sequential eruptions in the northern half of the island opened up Krakatoa's magmatic vents to the ocean, allowing vast quantities of seawater to vaporize upon interacting with the magma. The gigantic pressures from the expanding vapor, in conjunction with the explosive magma, culminated in a climactic third eruption. Hardly an eruption. 200 megaton detonation of hydrothermal pressure, pulverizing the island in an instant. And what the explosion didn't destroy, the collapsing caldera quickly swallowed. The result? An immediate pressure wave recorded at 172 decibels in Jakarta, one of the loudest sounds ever experienced by people. Tsunamis 100 feet tall, fanning out across the Sunda Strait. The 2,500-foot tall Rakata, the tallest cone of the trio, sheared in half after its north face collapsed, exposing its central vent like an open wound. And an ash column, 80 kilometers tall. 80 kilometers. It's ridiculous. Not even the largest mushroom clouds reach that high. It's at a point where only a handful of clouds out there top it. Noctilucent clouds, vapor trails from spacecraft, and thermospheric nuclear tests. And this is impressive enough, but one has to remember that this is just the ash column. In reality, a small slice of the total ash cloud produced by an eruption. In 1883, it would have been difficult to properly determine the full extent of the cloud, especially when the area beneath it is the site of one of the worst natural disasters of the century. And this was the case for most large eruptions of the early 20th century as well. But beginning in the 60s, something changed. Weather satellites, while designed for monitoring traditional meteorological events and storm complexes, are unsurprisingly also quite good at observing volcanic eruptions. It's really just a matter of catching them when they happen. The lengthy blackout times of normal polar orbiting satellites made this a bit tricky. But by the mid-70s, geostationary satellites were going up, which could stare at a specific section of the planet indefinitely. The American GOES and Japanese GMS covering the Pacific were in a unique position to observe eruptions, a front row seat to the Ring of Fire. And it wasn't long before one did. The lateral blast of Mount St. Helens eruption meant a significant amount of the ash cloud pooled around it, completely burying the 4,600-foot tall mountain in a matter of minutes. The column rose until it slammed into the stratosphere and flattened. From the ground, it's an incredibly imposing sight, but from space, its full extent can be realized. A massive ash canopy, not unlike the anvil of a cumulonimbus cloud, close to 100 miles, 160 kilometers wide at its greatest extent. The cloud with distinct layers where wind shear took a hold of it, and the canopy itself elongated to the east by the upper atmospheric westerlies. The cloud persisted for a couple hours before the canopy was dissolved by said westerlies into a diffuse ash deck which would rain down upon significant portions of the United States and Canada. While not the largest out there, to have a large volcanic cloud like this so heavily observed was a first. and would serve as the leader in a trio of successively larger and more scrutinized eruption clouds. In 1982, a similarly sized eruption was produced by the Mexican volcano El Chichon. While not as extensively observed, the glimpses of it that were collected revealed an ash cloud of also similar size. However, it wouldn't be until over a decade after St. Helens that the prying eyes of a satellite would witness a significantly larger eruption. But when one finally did,
about 1:45 in the afternoon, just a blast. As we stood and we just watched our instruments for half an hour, and they were just pegged. They were just going as hard as they could.
1991 was a year of turbulence. The Soviet Union was imploding, the United States was exploding, and on the northern Philippine island of Luzon, a volcano was readying itself to create a bigger bang than either of them. As close to Manila as Fuji is to Tokyo, Mount Pinatubo. Not the grandest volcano out there, slightly smaller than Mount St. Helens, but sharing a similar fate nonetheless. Similar, not the same. On June 12th of 91, Pinatubo let loose in a series of eruptions which generated massive ash columns and pyroclastic flows. Unlike St. Helens and El Chichon, however, activity did not die down. In the following days, the eruptive activity persisted as magma continued to build beneath Pinatubo. And if only that were the extent of it. Much like with Odysseus in the Odyssey, the island of Luzon now found itself caught between Scylla and Charybdis. On the eastern side of the island, Typhoon Yunya, an equivalent Category 3 if rated as such, was primed to make landfall, and Pinatubo showed no signs of slowing down. Then on June 15th, with Yunya miles off the eastern coast, Pinatubo unleashed
a power greater than any
volcano in nearly 80 years. A VEI 6 eruption, sending tephra the size of boulders to rain down upon local towns and villages, and then pyroclastic clouds to sweep them clean. And what those didn't inflict damage to, the Lahars made sure. The ash cloud made quick work blasting through Yunya's outer rain bands, mixing the ash column with heavy precipitation and sending scorching mudslides down neighboring river valleys. And while chaos ensued below the typhoon's clouds, they themselves were quickly and quite literally being overshadowed. Pinatubo's ash cloud quickly rose to 40 kilometers in height, spreading out to a monstrous size of around 280 miles or 450 kilometers in diameter, and finally engulfing the comparatively small typhoon below it. But while the effects of the disaster would linger for months, some years, and the physical effects it had on the mountain still stand today, the integrity of the ash cloud would be brief. The same wind shear that was now beginning to degrade Yunya would take its toll, and the enormous cloud would disintegrate in a matter of hours, becoming an amorphous blob of dispersed ash which would rain down on Southeast Asia. Thus marked the end of the largest eruption in decades. And who knew just how many decades would have to pass before an even larger eruption would occur? And that really is the key to it. The only thing you can really feed the Earth to get it to go its own kind of nuclear. Time. No chemical, no material, no device. Just time. Well, that and heat. But for however heated global tensions were in 1991, At least we've cooled off since then. Hunga Tonga and its neighbor Hunga Ha'apai are two of the most inconspicuous islands in the Pacific. Funny enough, they are also as far from their nearest major city as Fuji is from Tokyo, the Tongan capital of Nuku'alofa. And compared to it, they really are just a pair of rocks out in the ocean, quiet and inactive. But the Tongan subduction zone to the east says otherwise, and in reality, Hunga Tonga and Ha'apai conceal a monster. The Hunga Tonga volcano takes the form of a small caldera complex, its base below the sea surface, and its rim only visible as the Twin Islands. Unlike Pinatubo, St. Helens, or Krakatoa, there is no large volcanic cone to signify a volcano. That's how it's been, and how it is today. But in 2015, that changed. After a series of eruptions early in the year as strong as VEI-2, ejecta formed a new volcanic ash cone and joined the two islands together. A volcanic cone initially predicted to be eroded away by the end of the year was here to stay for decades to come, and it seemed the Hunga Tonga volcano had finally made itself visible. But this was a ruse. This new cone, while striking in appearance, had manifested itself on the edge of the caldera. In fact, the vast majority of Hunga Tonga's recent eruptive history seemed to be these caldera rim ventilation incidents, while the main vent at its center waited. It waited not too much longer, and a brand new volcanic island that was supposed to last for decades lasted 7 years. On January 15, 2022, magma breached the caldera floor beneath 650 feet of seawater. Too shallow to contain the eruption and too deep to get out of its way, the water vaporized in an explosion which obliterated the new island. Nearby islands were first hit with the shockwave, then tsunami warnings, then heavy ashfall, as the immense cloud grew overhead. The explosion propelled ejecta high into the atmosphere within the hour, and the ash that could not follow fanned out, creating gigantic canopies which sculpted themselves along atmospheric boundaries. Larger than any thunderstorm anvil, any mushroom cloud head, and any other volcanic eruption of the previous century, the upper, more pronounced stratospheric canopy reached a diameter of 500 kilometers, while the lower canopy along the tropopause at 16 kilometers up spread out to 650 kilometers. That's 311 and 404 miles respectively. And towering above both of them, the eruption column, casting a shadow on clouds that were already 3 times higher than the cruising altitude of an airliner. In fact, the entire height from sea level of Mount Everest could rest on top of the upper canopy, and it still wouldn't be taller. The column would peak at 55 kilometers in height before descending, the tallest recorded since Krakatoa. And that seems to be the theme with Hunga Tonga. The endless comparisons with that infamous 1883 eruption. The destruction of an island, the hydrothermal explosion, and a shockwave which found itself circumnavigating the Earth, audible for thousands of miles. It's an interesting realization, then, that Hunga Tonga's explosivity was still only about half that of Krakatoa, with far less total ejecta. It does make you wonder what a cloud of that magnitude may have looked like. A cloud never quantified, only witnessed. It's at points like these where size starts to lose its perspective a little bit, where heights become so ridiculous you can only really compare them to each other, and diameters so big you have to size them up against whole countries, or islands, or the Death Star. Hunga Tonga is not a very large volcano. It's only a couple miles across. Nor is Krakatoa, Pinatubo, or really even Mount St. Helens. But look what they can become. It's somewhat poetic that the largest shield volcanoes on Earth produce comparatively minuscule eruptions. Even the largest lava fountains struggle to break 2,000 feet, which, yeah, is tall, but it's not stratospheric ash plume tall. Hawaiian eruptions, while carrying destructive potential, are mild, downright gentle by those standards, most not even registering as VEI 1s. However, basaltic volcanoes without the ability to explode like their stratovolcanic cousins do have one trick up their sleeves. The mantle plumes which generate hotspot volcanoes, such as Hawaii, act in a very similar manner to atmospheric clouds, ash plumes included. When they reach the hard lithosphere of the tectonic plates, like a cloud with the top of the troposphere, their tops spread out, and they can be far more intense than those we see today. There is geologic evidence for absolutely titanic eruptions, not in explosivity, but in extent. Eruptions that span centuries and continents, that could create entire seas of flowing basaltic lava. Thankfully, humanity has never encountered one of these, but the evidence they left behind is on display for all of us to see. And even though the violent explosions of stratovolcanoes and volcanic calderas take the spotlight now, the full extent of their influence is nonetheless something to behold.